It's a pleasure to be on the webinar this morning, and I thank Christian. And I have to do a special shout out to a colleague of mine, Anna, who took my very bland slides and made them into something very colorful and pretty. So this morning, what I'm going to do, or today, I'm going to talk about the rice husk biochar product that we are manufacturing and the applications we're using for the biochar. So who is Glanris? Well, Glanris, as the first bullet says, is a manufacturer of patented sustainable hybrid water purification media made from rice husks. We're located in Memphis, Tennessee. Memphis is in the southwest corner of Tennessee, adjacent to Mississippi and Arkansas. And as you will note from this map, about 50% of the rice produced in the United States is produced in Arkansas. So literally across the river from Memphis, we have a large supply of rice husks available for our production. The other major locations for rice production in the United States is California and Louisiana. So as Christian has asked, we should start with a little preamble of what is biochar. Biochar is a form of charcoal produced from biomass. It's typically rich in carbon and other minerals. It's produced by pyrolysis process, usually the slow burning of the material. It's typically highly porous, resistant to degrading. And the beautiful part about biochar, at least I find this very exciting, is the fact that the biochar can sequester carbon. It could pull carbon from the atmosphere and sequester it if it's buried or incorporated in some type of material for thousands of years, thus removing it from the atmosphere. Biochar is typically used as a soil amendment, as I just mentioned, but it can be used in other applications. As others on this program have stated, it can be used in concrete, it can be used in asphalt, it can be incorporated into plastics, it can be used as a food source, a supplemental food source for animals. There's a lot of potential applications for biochar. We're using it for water treatment. And and as we go forward, you're going to see, you're going to learn the other great things we do with the char. In this photo here, we have a picture of the rice husks, and then this is the product we produce. Now, traditionally, biochar is produced, again, as I mentioned, by the slow burning of materials. If you look at the picture on the right, those are coconuts. I've had the great blessing of being able to travel many times to the country of India and also to Sri Lanka. And if you go to the Tamil region of India or Sri Lanka, you'll see many of these pits, as you see here, and coconut shells are thrown into these pits. They're caught on fire. They're covered with soil, allowed to smolder, and then there's the release of greenhouse gases and CO2 into the atmosphere, which continues pollution. Plus, it's an old uncontrolled charring process. Also, as you can see in the lower picture, there's the frequent open burning of agricultural waste to eliminate it. Now at Glanris, we actually have a patented process for the production of biochar. The equipment we use is right here. It's a rotary kiln. It's a custom designed piece of equipment for our use. There's minimal air introduction to this unit. Again, as I mentioned, it's a controlled pyrolysis, and we destroy any greenhouse gases or oils so we don't emit them to the atmosphere. We believe, based on our math, that we're sequestering about 50% of the CO2 or the carbon contained in the rice husks. So what are rice husks? Well, they're the protective coating or shell over the rice grain. So you can see in the picture here some growing rice. Actually, in the background, I have growing rice. So you can see the husk here. Here's another example of husks. And typically the husks are about the third of the weight of the entire white rice grain and are made primarily of silica and lignin. So why rice husks? Why are we interested in it? Well, one, we have a ready local source, as I mentioned, across the river from us in Arkansas. About 50% of the rice in the United States is produced, but it's also grown around the world, and there's a huge quantity of rice husks produced. The rice husks are a waste product, so they have no other value. They're typically burned or thrown on the land or landfilled, and when they're burned or landfilled, they're creating greenhouse gases and contributing to the degradation of the environment. Ultimately, as we said, our goal is to sequester this carbon and remove it from the atmosphere. And one of the beauties of our applications is when the product is exhausted, it can then be deposited in a landfill and the carbon would stay sequestered for thousands of years. Now, what's the advantages of using our media or this biochar rice husks? Well, it's a hybrid media. It's a designer media. It has both activated carbon functionality and ion exchange functionality. Because it's a waste product, it's cheap. It's available at a low cost, and of course, we sell at a low cost. I'm going to be presenting some data later on that shows that based on studies we've done, it operates over a wide pH range. Because of the density of the material, it's lower cost for disposal. As I mentioned, it has ion exchange functionality, and some of the work we've done has shown that the media can be regenerated without harsh chemicals. And again, the other beauty of this technology that we have, as we mentioned, rice is produced all over the world. So there's the ability to use our process locally anywhere on the globe. Uh-oh. Sorry, my machine froze. Let's see. The advantages of our technology, it's effective in the presence of oils and grease, and we'll present some data for that. Again, it's low cost. It's a light media. It can be used as a replacement for ion exchange resin and activated carbon. It's a small footprint, and I know you're going to get tired of me saying this, but it's 100% green and sustainable. This picture on the right side of the screen is our product. It's black strand-like particles. We can mill this material and produce it in any particle size. It has bulk density as shown on the screen, whether it's granular or milled, so it's fairly light. I'm going to be presenting data in a few seconds that shows that it's effective over a wide variety of pH ranges for metal removal, and it has a capacity of about 6 to 10 milligrams per gram for metal removal. Most importantly, at least in North America here, is that it meets NSF ANSI 61 for extraction requirements, so it allows it to be used in drinking water applications. In addition to cation exchange and absorption capabilities, we believe that our material also can remove contaminants from water by complexation, co-precipitation, and electrostatic attraction. As I stated earlier, Glanris is a relatively new entity. We've been around about 3 years. We have a brand new laboratory with brand new equipment, state-of-the-art equipment. We also have relationships with various universities that we're conducting research with, and we're a member of the International Biochar Initiative and the US Biochar Initiative. Typically in our lab, we run isotherms, as you can see in the pictures here, either column or a batch isotherms. And then we also have pilot scale capabilities, and we've done a lot of pilot scale work, and we provide on-site analytical analysis to demonstrate the performance of the media. Now what I'm going to do is go through a series of slides that demonstrate the performance of the media. Here we have removal of copper from water. This is a column study where we had about 27 grams of media in a column. We passed either 2 part per million or 0.2 part per million of copper solution through the column at a constant flow rate of 20 mils a minute. And when we reached 99% removal of the copper, we stopped the test. And as you can see, over a wide variety of pH ranges, we have functionality for removal of the copper. Ultimately, at about pH 7 in this case, we're getting about 10 milligrams per gram of copper removal from the water solution. In this study, we looked at the ability to remove nickel from water. Again, this is the same conditions. Again, we're around 10 milligrams per liter. And again, you can see that we have very, very good capacity to remove nickel over a wide variety of pH ranges. Here's another set of studies, again, done the same exact way. This is with zinc. And once again, wide pH range, significant reduction of zinc from a water solution. And lastly, we have a test here with looking at hexavalent chromium. Again, same test conditions. Just sorry to be redundant, but wide pH range that we operate under, and we can get to a maximum, again, of about 10 milligrams per liter at about a neutral pH. As I mentioned earlier, we have demonstrated in the field and in the laboratory that our media has the ability to continue with ion exchange functionality without fouling and continue to be able to remove metals from water. Typical ion exchange media does not have this capabilities. Here's a study that was done where we looked for copper removal with increasing concentrations of stamping oil in the solution. And as before, when we reached 99% reduction of the copper, we stopped the test. And as you can see, as the concentration of stamping oil increased, our efficiency decreased for removing copper. But overall, I mean, this performed very well in its ability to take a copper out of solution, even in the presence of an oil. Here is a lead reduction study. As I believe all you know, lead in drinking water is an issue. There's been a lot of problems with that here in North America, especially with the aging infrastructure that we have. So we conducted 2 tests. This one here is at pH 6.5, using 150 parts per billion of lead challenge, which is the NSF standard 53 lead challenge. And as you can see in this study, we were able to, again, with 50 mils of media or 27 grams, we're able to get about 1,000 liters of capacity before we started to see breakthrough of the lead solution. When we looked at particulate lead, again at pH 8.5, we also did over 1,000 liters of lead removal. And again, these are really fantastic results and show the ability of our material to remove contaminants such as lead from water. Now, we also, as I said, did some field trials, and so I'm going to show you some of that data right now. This is a field trial that was done in an auto parts manufacturing plant in the Midwest. They currently were using bone char as their media of choice. And from the data that you can see on the screen, when they looked at total suspended solid, manganese, zinc, and nickel, our product outperformed the current technology they were using for the contaminants that they were concerned about. And again, because our material is less dense, it's less costly to dispose of the material when the disposal is by weight. Here's another auto parts manufacturing plant where they used a variety of technologies to remove contaminants. The list of contaminants is the same here. Once again, we outperformed the existing technology. So now we have a one-step treatment technology that's replacing multiple technologies that are deployed for removing the contaminants of concern. The last field study was a medical device company where they were doing chromium plating. They were using ion exchange media at $625 a cubic foot to remove metals from their waste discharge so that they could comply with the US EPA regulations. Again, when we were able to replace their existing ion exchange media with our technology, and once again, you can see that the removal of the copper, nickel, and chrome from their wastewater, our technology exceeded what was currently being done at a significantly lower cost, not only for the product, but for operational costs. So what media applications do we have for Glanris? Well, as I stated, it's a direct replacement for ion exchange media and for granular activated carbon. It can be used in a variety of applications, all water related, wastewater, drinking water, environmental remediation, etc. And the applications basically are endless. There's a list here. But besides metal removal, we're looking at it for organics removal, chlorine, BOD, COD, color, and odor reduction. So in summary, I think I'm doing pretty good on time, Christian. On summary, Glanris is a designer biochar produced from rice husks. It's a hybrid media because it has multiple capabilities. It's green, which is near and dear to my heart, so it's sustainable. There's no harsh chemicals used to produce it, and it can be removed a wide variety of contaminants from the water at a relatively low cost. And I just want to point out that we're only at the beginning. As I stated, our company is only a few years old, and that there's more to come from us as we're beginning to add more functionality to the media and looking at other applications and of course, continually improving the technology. So I want to thank you, Christian, for inviting me today, and I want to thank you all for being on the call. Do we have any questions?
Thank you very much, Frank, for your presentation. Really interesting. And yes, you got some questions already.
Okay.
So the first one was from Jorge, who was asking about your paralyzer. So you mentioned the rotary kiln to produce biochar is patented. What would be the main innovation about it, and how big is the reactor in kilograms per hour?
Oh, okay. Now that I don't know the kilograms per hour. That's something I could get back to you on. And dimensionally, truthfully, I believe the kiln is about the rotary kiln part. I believe is around 8 feet, 8 or 10 feet. Again, I'm sorry, I'm North American. We use English units. And it's a custom design. What's unique about it, it's a custom design unit for us. We have trade secrets used to design the equipment and how we operate it. So there's really not much I can say about it and how we control the air intake, et cetera. But it's not an off-the-shelf product.
Okay, so the next question was from Luca, I think. No, from Kwanasa. Do you know the specific surface area of your biochar?
Well, it depends on how you measure it. We're using a BET method where we're using a refrigerant gas, R232, I think it is. And our surface area is around 250 square meters per gram.
And a follow-up question from myself. So what's the temperature you're using for the pyrolysis?
Per our patent, we're using around 400 degrees Celsius.
Then Luca was asking, what do you do with your biochar after the water treatment?
Oh, well, after the water treatment, it can be disposed of in a landfill, and thus the carbon that's sequestered in the biochar will be permanently encapsulated in the soil and removed from the atmosphere.
Have you done anything, any tests on desorption properties of your char?
Well, we can regenerate the material so for metals reduction performance. So we can take and remove the metals from it. And we're in the process of doing the testing that you just mentioned. In the United States, we have to do something called a T-clip test to make sure that we're not losing the materials to the environment, and that's in process right now.
So I have to limit the questions now to a couple of them because there are a lot of them going on. Arvind Kumar has raised his hand. Do you want to ask a question? Arvind, are you here?
Hello.
Yeah.
Hello. Thank you so much for very interesting talk. Please excuse me. I'm a new to biochar field. I have just a question about the first slide where their professor have mentioned that the biochar is resistant to degradation. But I have read one paper where they are mentioning that biochar can be degraded or decomposed via biotically or abiotically. So please explain the stability of biochar.
Oh, so you said it could be decomposed in what way?
It can be degraded biotically or abiotically, like
Okay.
using microbial degradation or oxidation and dissolution.
All right. Well, first of all, I'm not aware of that. I know all the papers I've read, and the foundation of the biochar industry is that the biochar, once it's sequestered, is stable. There's been research work done that's identified biochar in Brazil that's been in the ground for thousands of years, and it is not degraded. I know in agricultural applications, one of the benefits of biochar is that it can foster microbial growth, which is what I'm assuming you're addressing, and help the nutrient conditions of the plants so that they can grow. So I'm not aware of it degrading. I'm only aware of its benefits and its long-term life in the environment from not degrading.
Okay. Thank you so much, sir.
You're
Very
welcome.
interesting.
Sorry about that.
Two short questions, two more questions. So one was, do you have any vital research papers that can be shared or that we can find online from Glanris?
No, we don't right now. Actually, that's something that we're planning to do this summer to get a research paper out, but currently we don't have any studies. We have, like I said, we have patents filed globally, We have one issued in the United States and another in China and others pending. So we've been focusing on intellectual property.
And then there was one question from Pierre. Have you had any trouble with char releasing contaminants in the water like PAHs when you're doing the heavy metal adsorption?
No, we don't have experience with that yet.
And then a last question from myself. Is your char floating?
Floating?
Floating on the water, or is it?
No, it will get saturated and settle. I mean, it's like anything else, but it will settle.
Okay.
Typically, we put it in a column application. Right now, it's in a packed bed.
And then there was one more question from, where is it? Did you compare the different types of biochar with your product, and what was the difference in the absorption capacity of various metals? So did you compare your biochar to other biochars?
We haven't gotten that far yet, no.
Okay.
We do know that other biochars can remove metals. I mean, there's a lot of research papers out there, but we haven't compared them.
Okay, thank you very much.
You're welcome.
If there are any more questions, maybe Frank can take a look at the chat if there's anything you can add there.
I will.
And otherwise, thank you very much, Frank, for your presentation.
You're welcome. Thank